All right, welcome back, everyone. So for our second talk today, we have Jeremy Miller from Purdue, who will tell us about Rognes's connectivity conjecture and Steinberg modules.
Yeah, thanks for having me. These are mostly slides from an hour-long talk, which I then added some additional slides to, so we'll see how this works in a 45-minute talk. Yeah, so I'm going to tell you about a connectivity conjecture, what it has to do with Steinberg modules. So this is mostly older work, and then time permitting, there's like a slide on some follow-up projects that I'm working on now, but we'll see if I get there. Okay, so probably in this audience, I don't really need to motivate algebraic K-theory, but given a ring, K-theory is a spectrum that codes a lot of information about the ring. I mean, the K groups are the homotopy groups of the spectrum. K0 is the Grothendieck group of finally generated R modules. There are a lot of deep connections to number theory. If you look at the integers, vanishing of K4I of Z is equivalent to the Kummer-Van Dyer conjectures, which is a conjecture about divisibility of certain class groups. K groups are related to special values of L functions. They also have lots of connections to manifold theory through surgery theory, such as calculations in like diffeomorphism groups of spheres, relies on K theory, and it's this huge story. So I'm going to tell you a little bit about John Rognes' strategy for computing K4 of Z, which he showed was the zero group. So the strategy is you find a nice filtration of the K theory spectrum, and then you compute the homology of the associated graded of the spectrum in as big of a range as you can. And then that gives you a spectral sequence that lets you compute the spectrum homology of the K theory spectrum. And then you use, one of the ways of going from homology to homotopy groups, like the atom spectral sequence, or like just looking at Postnikov towers and Serre spectral sequences. So this is hard and doesn't let you this is a reasonable strategy for computing things in a range, but things get more and more complicated. Okay, so let me tell you what the roughly where the filtration comes from. So there's a thing called the Waldhausen S dot construction, and it gives you a model of algebraic K theory built out of simplicial sets coming from diagrams of R modules. And let's say R is a reasonable ring where you know what rank means, like maybe R is a PID. Then you can filter your simplicial sets by just looking at the portion of where all of the R modules that appear have rank less than or equal to n. So this gives you a filtration of the K theory spectrum. In this, by filtering the S dot construction model of it by rank. And in the 90s, John Rognes identified the associated graded in terms of this simplicial complex called the common basis complex. Okay, so from now on, I'll assume the ring is a PID. A lot of the statements will work in more generality, but it'll be easier. Yeah. So this simplicial complex that shows up in the associated graded is the of the the rank filtration. It's called the common basis complex, and so there's one for each n, and the vertices of the nth common basis complex are proper non-zero summands of r to the n, and a collection of summands will form a simplex if there is a basis of r to the n such that each of the summands are a span of some subset of the basis. So I've drawn an example of a simplex. So if v1, v2, v3 is a subset of a basis of r to the n, then span of v1, v2 is a vertex, span of v1, v3 is a vertex, span of v3 is a vertex, for example. And these three vertices form a simplex in the simplicial complex. Yeah, so maybe we'll get to know this, what it means for things to have a common basis a little better. Yeah, so let's consider span of E1 and span of E1 plus 2E2. Both of these are, let's say we're taking the Z span, then both of these are summands of Z squared. So a vector will span a summand if and only if the GCD of the coordinates is 1, and the GCD of 1 and 0 is 1, and the GCD of 1 and 3 is 1. So these two span summands, so these two give vertices of the common basis complex for Z squared. But there is no edge connecting them because there is no basis of Z squared that spans one of the vectors, or where one of the vectors spans span of E1 and the other one spans span of E1 plus 3E2, and the obstruction here is the determinant of the associated matrix is 3. Yeah, so like the sum of the two summands isn't a summand; it's index 3 in Z squared. On the other hand, if you're working over Q squared, then they would have a common basis property, and if you're working over a field, any two subspaces have the common basis property. But the common basis property is still an interesting property over fields once you have more than two things, once you have more than two subspaces. So if you consider three two-dimensional planes in three-dimensional space, you can ask, let's say they're all distinct, you can ask, when do they have a common basis? And the answer is if the three of them intersect at the origin. Oh yeah, so I mean, everything is subspaces, they're not affine subspaces. Yeah, so, but you could have three planes that intersect at a line, for example. Three distinct planes in three-dimensional space can intersect at a line, and those wouldn't have the common basis property. There's no way of finding a basis for F3 such that any two of the planes are a span of a subset of that basis. But if they intersect at a point, you do have this. What do I want to say? Yeah, you should sort of think of the common basis property as a condition that means your vector spaces behave like sets. So vector spaces have the inclusion-exclusion property if you have two of them. Like the dimension of the sum of two subspaces is the sum of the dimensions minus the dimension of the intersection. But if you have three subspaces, the dimension of the sum of three subspaces is not the sum of the dimensions minus the dimensions of the double intersections plus the dimension of the triple intersection. But if they have a common basis property, then that'll hold. Okay, are there questions? Yeah, okay. So, okay, it's just the simplicial complex. Yeah, so this simplicial complex is the simplicial complex of things having a common basis property. And um, uh, John proved that the associated graded of the rank filtration of this K-theory spectrum is given by the suspension spectrum of the homotopy orbits of GLN acting on the common basis complex. If you do this right in a base sense, or in other words, the homology of the associated graded is, so it's the hyperhomology of GLN with coefficients on reduced chains in this simplicial complex, or in other words, it's just the reduced equivariant homology of this simplicial complex. So if we understand the simplicial complex better, then we, can understand algebraic K-theory better. And in particular, he conjectured that the common basis complex is 2n minus 4 connected if R is a Euclidean domain or a local ring. And this conjecture implies a vanishing line of the E1 page of the spectral sequence converging to the homology of the algebraic K-theory spectrum. So, spectral sequences are easier if there's a bunch of zeros. Yeah, and in particular, currently, if we knew the conjecture was true, or at least true in a range for Z, it would imply that K12 of Z is 0. This is currently the lowest K group of the integers. That's unknown. Oh yeah, another remark, the dimension of this complex is super big. It's exponential in n. But John proved the homology vanishes above dimension 2n minus 3. So the conjecture is equivalent to the simplicial complex being homotopy equivalent to a wedge of 2n minus 3 spheres. Yeah, and it's not that hard to construct alternate models of this homotopy type that are simplicial complexes of the correct dimension. But I still like this model. Okay, so what was known? So John proved the conjecture for fields for n less than or equal to 3. I think he proved the conjecture, or slash it was, maybe just like you have to cite existing literature to prove the conjecture for n equals 2. Or John at least was aware of that. And then Soren Glacius, Alexander Coopers, and Oscar Randall Williams proved the connectivity after taking homotopy orbits. So they proved the reduced equivariant homology of the common basis complex vanishes in the range predicted by the conjecture. So for infinite fields, so this is for infinite fields, this is enough to get the vanishing line for algebraic K-theory. Yeah, and then our result is that the conjecture is true for all fields. So we don't need infinite fields, and we yeah, so it's sort of a lift of Soren, Sander, and Oscar's result. And our proof is inspired by their result. You might say, okay, well, you don't tell us anything new about the spectral sequence for infinite fields, and you don't say anything, and the K-theory of finite fields is fairly well understood. So what is the point? We got into this from the theory of Steinberg modules, which will take up the rest of the talk. But yeah, I mean, K-theory is how I decided to sell it, but it's not my motivation. Yeah, so the main thing I want to tell you is sort of like what does the reduced homology of this simplicial complex mean? Like what is it measuring? And the answer is the homology of this common basis complex is measuring the commutative homology of this ring, this commutative ring that I'm built out of Steinberg modules that I'm calling Steinberg R. And yeah, so the large portion of the rest of the talk is to unpack what do I mean by the commutative homology of this ring built out of Steinberg modules. Yeah, so first I'll tell you what I mean by commutative homology, and then I'll recall the definition of Steinberg modules. Okay, so if I'm running out of letters for rings because, but yeah, okay, so so let lambda be a graded ring, then Q lambda is defined to be the co-kernel of the multiplication maps. So Q lambda is the quotient of lambda by products of things in lower degrees. Yeah, so this is this is indecomposables, like in the sense of rational homotopy theory. So if you plug in symmetric algebra or and then take Q, you get out V. Similarly, if you plug in a tensor algebra. And I'll let QL com be the left-derived functor of this functor from commutative rings to chain complexes. And the commutative homology is the the homology of this chain complex. So H0 measures the generators of your ring. H1 measures the relations. H2 measures the relations among the relations. You can also make sense of indecomposables for associative algebras. So the quotienting by products of things in lower degree gives you a functor from associative rings to modules or to abelian groups, and so you can take the left-derived functor of the the functor defined by the same formula, but now the domain is associative rings instead of commutative rings, and that defines the associative homology. So if you have a commutative ring, the associative zeroth homology and the commutative zeroth homology are going to be the same. They're both just going to be Q lambda. They're just going to both be the indecomposables. But in general, in higher degrees, the commutative homology and the associative homology could be completely different. And like I said, in degree 1, for instance, the associative homology is in general will be larger than the commutative homology because so H1 is measuring the relations. But if you have a ring and if you have a commutative ring and you want to describe the relations, the fact that the generators commute is already built in, and H1 com is just measuring the extra generators of your ring as a commutative ring, whereas H1 associative, you need to add extra, your ring. If you're writing a presentation of your commutative ring as an associative ring, you need to add extra relations declaring that the generators commute, and those the fact that those extra relations will can show up in H1 associative. Yeah. And I mean, another comment, the associative homology can be described as using Tor groups. So if you view lambda, remember lambda is a graded ring. Lambda 0 is the part in grading 0. You can view lambda 0 as you can view lambda as augmented over lambda 0. So you can so in particular lambda 0 is is a lambda module, and you can form these Tor groups, and the associative homology is just the with a shift is just the Tor groups of whatever, lambda 0, lambda 0, lambda. So if lambdas, if you think of lambda 0 as like the ground ring, then this is saying the associative homology. Or yeah, I mean, I don't. This is somehow this thing is at least the one of the things that might be called the Cazul dual of lambda. Yeah, so it's associative homology is naturally a coalgebra. But yeah, okay. And you can also make sense of if you could replace commutative and associative with an arbitrary operad and make sense of O homology for general operads. Oh, and you can replace lambda instead of being a discrete ring, you can make it a chain complex or a spectrum or whatever you want. Okay, so this is what I mean by commutative homology. Okay, so the theorem I mentioned earlier says that the homology of this simplicial complex that shows up in K-theory is the commutative homology of a certain ring. This ring is built out of Steinberg modules, so I need to tell you what Steinberg modules are. Yeah, so here's a sort of older simplicial complex. So the Tietz building. So the Tietz building of you can think of it as the subcomplex of the common basis complex, where you only where things will form a simplex if after reordering they're a flag. So after reordering, one summand is contained in another summand is contained in another summand, etc. Yeah, so if you pick if V1, V2, V3 is if those are a basis or at least a subset of a basis, then you get these 6 vertices in the common basis complex, and in the common basis complex they would span a 5 simplex. But here you only have edges if you have containment. So V1 is contained in V1, V2 and is contained in V1, V3, but it's not contained in the other ones. So you end up only having you get this hexagon instead of a 5 simplex. Yeah, and the Solomon-Tietz theorem says that when R is a PID, the Tietz building is homotopy equivalent to a wedge of spheres, and I just of dimension n-2. So if you plug in n equals 3, this is a picture of So this says that the 3-dimension the Tietz building, the third Tietz building should be a wedge of circles. So it should be a graph, or it's a wedge of 1 spheres, and this is an example of one of the 1 spheres. And the Steinberg module is defined to be the one interesting homology group, the one potentially non-vanishing homology group of the simplicial complex. Okay, so if it turns out that these spheres, their fundamental classes generate the homology of the Tietz building, so they generate the Steinberg module. So how do we generalize this? So if V is a basis, if bold V is a basis, then let SV be the subcomplex spans of subset of proper non-empty subsets of your basis. So that will give you a subcomplex of the Tietz building. It's homeomorphic to an n-2 sphere. It's isomorphic to a n-1 simplex minus its top cell, barycentrically subdivided, or maybe n simplex. I don't know. Whatever gives you the right dimension. Yeah. So inside the Tietz building are these natural spheres coming from bases, and we so these spheres are called apartments, and the fundamental class of these spheres are called they're called apartment classes, or I guess the image of the fundamental classes of these spheres in the homology of the Tietz building, so in the Steinberg module, are called apartment classes. And okay, it turns out that these are oh well, I guess when R is a field, these classes are generate the Steinberg module. Yeah, so there's a map from the n Steinberg module tensor the m Steinberg module that on if you have a apartment class associated to a basis of Rn, and you have an apartment class associated to a basis of Rm, then you can this lets you construct a basis of Rn plus m, and and this map gives you a map of this gives you a map from Steinberg n tensor Steinberg m. Oh, I guess I didn't say the codomain of the map. Where's oops. This is supposed to go to Steinberg n plus Steinberg m. Yeah, I guess it's not necessarily obvious that this is well defined, because there's definitely relations among these apartment classes, and these also don't give you generators if your ring isn't a field, but nevertheless, this extends to a well-defined map of well-defined map, and it makes the direct sum of all these Steinberg modules an associative ring. Okay, so the first problem is there's sort of two natural ways of viewing Rn plus Rm as Rn plus m, and because of this, it makes this product non-commutative. And yeah, so that and remember what is the theorem? The theorem is that the homology of the common basis complex is the commutative homology of this ring, and I just told you that the ring isn't commutative, so we need a slight fix for that. Where are we? Yeah, okay, so the solution is to work in a category of representations of a groupoid. So I guess this is often done, if any of you are familiar with like symmetric sequences, we're going to be doing sort of a GLN version of symmetric sequences and deconvolution. Yeah, so I'll let GLR or GLR is going to be the groupoid of all of the GLNs, and a GLR module is going to be a sequence of GLN representations, or equivalently a functor from the groupoid to abelian groups or chain complexes or whatever. Yeah, and if you're familiar with the sort of yoga of day convolution, this groupoid is a symmetric monoidal groupoid, so it endows the functor. It endows like functors out of this groupoid with a monoidal structure, or concretely, if you have these two sequences, if M and N are sequences of representation, so M gives you a representation of every single GLN, N is a representation of every single GLN, and how do you build a new representation of every single GLN? You sum, well, what is it in degree N? You sum over all ways of writing N as A plus B, and then you, another typo, this is an N. You take MA, tensor, NB, that's a representation of GLA cross GLB, and then you induce up. And I'm going to say a GL ring is a monoid object in this category. You can define commutative monoids in this category. You can define tensor products, or you can define commutative rings to be commutative monoid objects. You can define tensor products. You can find modules and tensor products over rings and Tor groups, etc. In this category of representations of GL. And now if instead of just like taking the direct sum of all the Steinberg modules, you instead view it as a representation of GL. So you say, okay, I have this functor from, or I have this sequence of GLN representations, and in degree N, it's going to be the nth Steinberg module, the homology of the nth Tietz building. Then in this categories of representations of a groupoid, this thing becomes commutative. So like if you look at the formula is the formula for this product. Draw, yeah, okay. The typo persists. The formula was you take a basis here, Vn, you take a basis here, and then you get a basis here. That was the product, and once you sort of build in the GLNs into your category, all of a sudden this formula becomes commutative, or it's skew commutative. So if you put the Steinberg module in the correct grading, like if you view it as a it's the n minus second homology of something, so it shouldn't be in whatever. If you get the gradings correct, then it's commutative. Okay, and so now the theorem can be parsed. So we prove that the reduced homology of this common basis complex, so the thing that shows up in the stable rank filtration of algebraic K-theory, is the commutative homology in this. Now we're in this category of representations of a groupoid world of this generalized ring built out of Steinberg modules. Okay, so what is any questions? Okay, so I guess the original conjecture, so this holds for all PIDs. The original conjecture says for fields, this simplicial complex, our theorem is that for fields, this simplicial complex is highly connected. So how does this interpretation with commutative homology help you? So first, I guess next thing we're going to need is a description of the EK homology of the Steinberg module for all k. So I'm going to describe these simplicial complexes that I guess are desuspensions of things introduced in John's paper. So the TNK, it's going to be the subcomplex of you take the Tietz building, you join it k times, and then you just look at the subcomplex consisting of flags of I guess joins of flags of things with a common basis. So for example, if you took like span of E1 contained in span of E1 plus E2, that's in a Tietz building. E2 is in a Tietz building. E1 plus E3, I guess this should all be, these brackets should be span. Span. Then this is an element of the threefold join, but it's not a simplex because the common basis property doesn't hold. Like you're going to need you're going to need E1 in your basis, and you're going to need E3 in your basis, and you're going to need E1 plus E3 in your basis, and they're linearly dependent. On the other hand, if you're working over a field and you're only looking at the T2 building, then it's just the join. So this is the fact that, or it's a generalization of the fact that if you have any two subspaces of a field, they'll have a common basis. If you have any two flags of subspaces of a vector space, they'll have a common basis. Yeah, this is like a classical fact. Yeah, and then if you like interpret it properly, John proved that the co-limit of these TK buildings is their union is the common basis complex, and we prove that, or our theorem generalizes to say that the homology of these simplicial complexes measure the EK minus 1 homology of the Steinberg module. So E1 is just the same thing as associative. E infinity is the same thing as commutative here. It's not because I'm working rationally, it's because the symmetric groups are subgroups of GLN. So when you're in this world of representations of a groupoid, you don't really see the difference between commutative and E infinity. If your groupoid is bigger than the symmetric groupoid. Yeah, so the theorem is that John's conjecture is true for fields, and the way we prove it is well, first, if you have vanishing for EK homology, you get vanishing for EK plus 1 homology. You can see this by saying like EK homology can be computed by a k-fold bar construction. So to get EK plus 1 homology, you just sort of do a bar construction on the chain complex that computes EK homology. And if you have a chain complex with a vanishing line and you do a bar construction on it, the vanishing line can only improve, like the zeros stay 0 in a spectral sequence. So in particular, vanishing line for associative homology implies a vanishing line for commutative homology. And the commutative homology is the reduced homology of the common basis complex. So that's the thing we want to show is 0. It's easy to see that these simplicial complexes are simply connected once n is big. So the conjecture is equivalent to of vanishing of homology. Yeah, so now all we need to do is check that the associative homology vanishes in a range, and the associative homology is computed. This is the only place where we use fields. The associative homology is computed by this E2 building, and in the field case, it's just a join of two copies of the Tietz building, and we know the Tietz building is highly connected. So a join of two highly connected complexes is highly connected. Yeah, so this is how, somehow it turns out that like the hard part in the proof is understanding sort of algebraically what these simplicial complexes mean. And then once you know that, then connectivity is reasonably straightforward. Yeah, so I mean, you get a corollary that there's a spectral sequence with E1 page, the E infinity homology of now here it's like an actual E infinity algebra where you take the Steinberg mod, you basically take a chain complex that's computing this by Steinberg homotopy orbits GL. I just mean a chain complex whose homology. So homology of this is the same thing as big O plus homology big O plus n homology GLN coefficients in Steinberg. And yeah, so you get this, now it's a actual E infinity algebra and chain complexes whose E infinity homology is the E1 page of John's spectral sequence. It also tells you that for F of field, the Cazul dual of this, that tells you that this Steinberg ring is Cazul, and its Cazul dual is given by Steinberg, tensor Steinberg. Yeah, and that somehow this has some interpretation in terms of polylogarithms, but I don't know that much about that. Oh yeah, so let me just end with like 1 minute on new results. So in joint work with Benjamin Bruck and Kevin Piterman, we proved sort of the analog common basis complex for a free group is 2n minus 3 connected. So if you take subgroups of a free group with the property and things form a simplex, if there's a basis for the free group such that all of your subgroups are generated by the subsets of your basis. So we proved sort of a free group version or like where you're, in other words, you replace GLN with odd FN. The out FN, the OUT FN version of this simplicial complex has equivariant homology given by graph homology. So we're sort of working on that. I mean, it would say that graph homology is the equivariant homology, is just the equivariant homology of out FN. And we're trying to sort of think like what our result says, if our result says anything about graph homology with a mark point. So yeah, that's one direction we're working on. Oh yes, also it'd be interesting to relate it to this like graph spectral sequence, but that appears in recent work of Brown, Chan, Galatius, Payne. Another thing you can ask for sort of symplectic analogs, and as far as I can tell, like rank filtrations of symplectic K theory are going to be boring and aren't going to be highly connected. But if you look at rank filtrations of the homotopy fiber of like GLN K theory mapping to symplectic K theory, that I think that'll be interesting, and sort of simplicial complexes like the ones John discovered will start showing up. Sort of in this direction, we computed that the Cazul dual of symplectic Steinberg modules are, or that the symplectic Steinberg modules are Cazul, and their Cazul dual is basically the GLN Steinberg module, which is sort of a weird result. And yeah, so like this should say that there's a spectral sequence whose homology is symplectic groups with coefficients in the GLN Steinberg module that converges to some delooping of the homotopy fiber of the map between GLN K theory and symplectic K theory, but we haven't sort of worked all of that out yet and figured out what simplicial complexes show up there. Oh yeah, that's all oh, and then here's a picture of an apartment building that I used to live in. That's all I have to say.